Very good morning to everyone present here. First of all, I would like to thank the organizing team for giving me this wonderful opportunity. Thank you, team. And before getting into the topic, let me introduce myself. I am Dr. Jayakrishan Sundarraj from India. I am working as an associate professor in the Department of Mechanical Engineering at AIM College of Engineering and Technology, Tamil Nadu, India. And my topic is an intelligent vibration-based approach for defect detection in friction stir welding. Actually, I think most of you know what is friction stir welding. Friction stir welding, before what I have done is, friction stir welding is a solid-state joining process widely used for aluminum alloys due to its excellent joint quality, low distortion, and superior mechanical properties. And while doing the process, the possibility of defect which we are getting is air voids and cracks may be there, tunnel defects and tool breakage can occur during the FSW process. So what the thing we have done is, whatever the signals can be obtained from the defect workpieces, we are going to observe that defect signals and we are going to stop the machine where it is. And conventional inspection methods are typically offline, time consuming and unsuitable for real-time monitoring. So only we have came for this online condition monitoring. Vibration signals generated during FSW provide valuable information about the welding process. The work proposes an intelligent vibration-based approach for the real-time detection of air gaps, defects and tool breakage. So the main thing we have considered is air gaps, where we are getting the air gaps and how the tool breakage signals are captured. The main objective of my work is to develop an intelligent vibration-based monitoring system for friction stir welding using an accelerometer sensor to acquire vibration signals. To investigate the vibration characteristics associated with defect-free welding and air gap defects and tool breakages. So what we have done is, actually we have selected so many parameters. And the main three parameters are the speed, feed and tool depth. We are considering these three main parameters for doing this operation. To evaluate the effectiveness of vibration signals analysis for the real-time detection and differentiation of defects during the FSW process. So this is the FSW process introduction. And FSW is a low heat input solid state welding technology especially suitable for low melting alloys, metals such as aluminum and magnesium. Here you can see it is a non-consumable rotating tool is pushed into the workpiece to be welded, and then central pin or probe followed by the shoulder is brought into contact with two parts to be joined. This FSW process is mainly suitable for butt joints. It is not suitable for T and F corner joint. We are not going to use that. The main type of welders we are going to use in the butt joint. And pin, it may be threaded pin or probe. It can be a threaded pin, or here we have not. We have used only non-threaded probe. Shoulder is there. The shoulder, here you can see in FSW cylindrical shoulder tool with a profile with threaded or unthreaded probe is rotated at a constant speed and fed at a constant traverse rate into the joint line between two pieces of sheet or plate material which are butted together. The parts have to be clamped rigidly onto a baking bar in a manner that prevents the abutting joint faces from being forced apart. Since overpressure we are going to give in the process, there is a possibility of removing from the die. So we are clamping rigidly to avoid those abutting joints. So this is schematic representation of FSW. And what we are going to do is the experimental setup and material selection. CNC milling machine is considered for this work. A small modification has been made for this process. Accelerometer sensors, that is vibration sensors we have used. The tool, C40 tool steel we have selected, and workpiece is aluminum alloy 6082. And this is the experimental setup. And here a tool is there, and workpiece we have clamped like that, and LabVIEW software is installed in that laptop. And accelerometer sensors, and this is vertical milling machine we have used. And parameters, selection machine type is CNC milling machine, controller GSK 980 CNC system. This is a 5-axis machine. Traverse space, it can travel up to 60,000 mm per minute. And application vibration monitoring, friction stir welding. And the sensor, accelerometer sensor we have used is Kistler, model type 8636 C50, sensitivity 100.5 megawatt, temperature range 0 to 65 degrees Celsius. And the tool we have considered is, already we have told the C40 tool steel. It is non-consumable tool, we can use so many times. And shoulder profile is flat, probe profile cylindrical unthreaded, pin diameter is 5 mm, and shoulder diameter is 15 mm, holding shank diameter is 20 mm and it is applied for friction stability. Actually, the pin will be, if we are considering two workpieces, the pin will be inserted in this two workpieces and it starts rotating. The shoulder produces heat so that it starts melting the workpieces. So after it moves, the workpiece is also getting melted and it will move along the path which we have fixed. This is the workpiece of aluminum alloy 6082 and the properties are there. And the chemical composition is according to EN5733, we have selected this material. And application of this alloy is high strength structural applications due to its excellent strength to weight ratio. It can be used in bridges, trusses and construction frameworks. It is widely used in transportation including truck bodies, trains and railway coaches. Suitable for cranes and lifting equipments because of its high load bearing capacity. Applied in marine and offshore structures due to its excellent corrosion resistance. Also used in ore skips, beer barrels, mill shafts, pressure vessels, storage tanks, machine components, aerospace structures, architectural frameworks, fixtures, jigs, etc. These are the main applications of this aluminum alloy 6082. So before these are the basic introduction about our FSW. Before getting to the work, we have tried so many trials for fixing the speed, feed and the transverse speed and the depth also. So we have selected from starting from the 600 RPM, we have gone to 1200. From that, we have selected only three parts here, shown here. And welding feed rate also we have selected from 30 to 90, 100 and like that. So in that we have shown 350, 60, 70 we have seen. And in that DAQ part and lapping software we have obtained the signals vibration frequency in the range of 10.2 kHz. And we have visually we can see the observation after completion of the process. So preliminary trial welds were carried out using different rotational speeds and feed rates to optimize the welding parameters. The weld surface quality was evaluated through visual inspection. After all considering all these parameters, we have observed that for the two rotational speed of 1000 and welding feed rate of 70, we have obtained excellent finish of the product. So based on this visual inspection of the weld surface, we have two rotational speed of 1000 RPM and a welding feed rate of 70 mm per minute produces the best surface finish. So we have considered that as an we have fixed this. This is the range of RPM 1000 RPM and the feed rate of 70 mm per minute we have fixed for the final test. These parameters were selected as the optimum welding conditions for subsequent experiments involving vibration-based detection of air gaps and tool breakage. So this is the signals captured from the software. The FSW process was performed at two rotation speed of 1000 RPM and a welding feed rate of 70 mm per minute. The vibration signals are acquired during the welding process as shown. So the graph shorted between the frequency and the magnitude. We have obtained a maximum magnitude of 9 m for frequency of 10.2 kHz. Indicates the stable welding. And under these stable welding conditions, we have obtained a defect-free weld. So this is the workpiece after welding process. So there is no air gaps or tool breakage or onion rings in this workpiece. So what we have done is we have artificially intentionally created some air gaps in the workpieces for some dimensions 3 mm, 5 mm, and 8 mm for 3 mm depth and 3 mm width. We have artificially created the gap. So it is shown in the figure here. The workpieces were intentionally prepared with air gaps. Set 1, air gaps with the dimensions 5 mm length, 3 mm width and 3 mm depth. And set 2 with two different dimensions for set 2 is for 8 mm length, 3 mm width and 3 mm depth. We have artificially created the gap in the workpiece. And set 1, during the FSW process and workpiece containing an artificial air gap of 5 mm into 3 mm width and 3 mm depth, the acquired vibration signal exhibited a maximum magnitude of 28 meters per second square RMS at 10.25 kHz under the welding parameters of 1000 RPM rotational speed and 70. So this is the completed workpiece. We can see the air gap in that I intentionally removed the place. And second, we have tried for this 8 mm air gap. So here we have obtained a maximum of 42 RMS at a frequency of the same 10.25 kHz under the welding parameters of 1000 RPM and 70. So here you can see the air gaps completely. So after the completion of the workpiece, the tool, some part of the deposited tool will be stored in the shoulder itself. So that should be removed for next process of. So for creating the tool breakage, we have intentionally reduced the speed and reduced the feed rate, and intentionally increased the speed of the tool, and we have given the tool plunge depth was increased, and the welding feed rate was reduced to intentionally induce tool breakage. The corresponding vibration signal acquired during the process is shown. It reaches up to 425 at a frequency of 10.25, beyond which the tool undergoes breakage. Why we have conducted this experiment is, actually this is the cost of for making the tool is also high, and the material which we are using is also time consumable. So to avoid that tool breakages, we have intentionally made this. If the signal reaches particular point, we can able to stop the machine or stop the processor. So this is the comparison of peak vibration magnitude for normal welding, air gaps and tool breakages. For smooth welding, we have obtained only 9, and for air gap of 5, we have reached up to 28 or 27, 28. In air gap of 8 mm, we have reached up to 42, and the tool breakage, it has went up to 425. So key observation from the vibration signal analysis is the chart clearly shows that the increase of amplitude from 9 to 28 microns shows the 5 mm air gap, and the increase of amplitude from 9 to 42 microns shows the air gap of 8 mm air gap. It is inferred that if the amplitude of normal FSW increases by 3 times, shows the presence of air gap. So it can be seen that the vibration signals has the potential to measure the air gap accurately. It is also inferred that the amplitude of normal FSW increases about 4.6 times higher, shows the presence of 8 mm air gap. A sudden increase in vibration amplitude from 9 to 425 clearly indicates the tool breakages, demonstrating that vibration signals can effectively detect catastrophic tool failure in real time. So we have considered these two air gaps and tool breakages, and the future work can be, we can have small holes, the online, develop a real-time online, and thermal, we are also considering for doing thermal effects also. Develop a real-time online defect monitoring system by integrating vibration sensors with machine learning algorithms for continuous defect detection using the FSW process. Extend the proposed methodology to detect additional FSW defects such as tunnel defects, voids, lack of penetration, glass formation, and casing faults. These are all the future ideas we are having. Validate the proposed approach for different materials, tool geometries, and weld parameters to improve the robustness and industrial applicability of the system. Integrate multiple sensors, signals, vibration, acoustic emission, force, and temperature to develop a hybrid intelligent monitoring system with higher defect detection accuracy. And these are the references. Thank you.
Okay. Is there any question?
And why we have not considered the weld strength is, that is a different area. We have concentrated morely on the online condition monitoring, what is happening during the welding process, and what all the things can be done, and when we can stop the machine. That thing alone we have concentrated here.
Actually, maybe several years ago, I studied on a AI study of a welding system on the aluminum contacts with mixed gases and also electrical discharge. Actually, the welding types or classifications are different with that one. I mean, you presented. What are the superiorities or the positive sides of your technique and other techniques also? Can you make a comparison on that, negative and positive sides?
While doing the process itself, we can actually, we have done the defect-free weld also. For that, we have captured the signals and we have set an image 9 microns. If it is normal weld, we can have the maximum signal as 9 mm. So if we are facing some defects in the workpieces, the range will be increased to some sort of values. If it is between the 3 to 5 mm air gap, or before the, after that, 5 to 8 mm air gap. If it is like that, we can stop, or we can identify what is the gap, amount of the air gap presence in that workpiece. Like that, we can identify during the process itself. That can be done after the process. While during the process itself, we can identify the air gaps presence.
So we can also apply this methodology to other alloy types?
Yeah.
with aluminum and other
Yeah, it can be-
mixtures?
It can be included.
Okay.
I have also one question. You mentioned your test setup work in 1000 RPM. So basically, any frequency above that RPM so means around roughly 16 hertz. How you trust them? Because you use FFT and some form of
Actually,
power signal here.
Actually, this is defect free will. So we have captured the signals at exactly 10. Now we have tried so many trial runs for fixing this speed and feed and transfer rate.
Yeah. My point is anything above that is highly dominated, but higher.
Higher signal.
frequency
What is the
of
higher
that,
signal we have captured? We have considered that.
Okay. Yeah. Great. Then maybe next presenter, Lin Ma.
Yes.
Please.
Maybe you can present the. Yeah. So Emirhan, can you make a photo?
You can also set up.
Yeah, in front of the.
Perfect. Thank you.
Set up for taking picture. Okay, our next presenter, Lin Ma, presenting a paper on finite element driven surrogate modeling for signal detection, electromagnetic force capacity prediction in 8-pole radial active magnetic bearing. Please, yeah.
Okay. Hi everyone. My name is Lin Ma and I'm from Tsinghua University, Beijing, China. And I will use the mouse to let you guys know where I'm talking about. It's a really long topic and it's basically a part of my big project. And what we just did in this paper is we trained a surrogate model, which is a finite element driven, and to predict single direction electromagnetic force in 8-pole radioactive magnetic bearings. And the first part is I will introduce the background and motivation of the paper. So what is an active magnetic bearing? And you can see from the left side, it's an active magnetic bearing, and I will call it AMB later. It's a non-contact bearing system that uses controlled electromagnetic force to support a rotating shaft. And here is a rotating shaft, it's a vertical. And this one, and this one is a radial bearing. It will control the shaft X and Y direction to make it centered. And here is the axial bearing. It controls the Z direction of the rotating shaft. And unlike the conventional mechanical bearings, the rotor is suspended without physical contact, which means there is an air gap between the shaft and the bearing. The rotor position is measured by sensors. Here, the red and white one. And the sensor will get the displacement of the rotating shaft and transfer the displacement signal to the controller. And the controller will adjust the coil currents through the power amplifier to keep the rotor centered. So which means the controller gets the displacement signal and input and output current, then to change the force, then to control the shaft in the middle. And application and advantage of the AMBs. So AMB can use in very high rotating machinery, like high-speed motors, compressors, turbines, and flywheel energy storage. And the advantage of AMB is it can use it in high temperature and high pressure resistance, and not require oil lubrication, and can be used in a high-speed rotating. So why electromagnetic force capacity important? All the advantages I mentioned before all rely on sufficient electromagnetic force, which means you do not have sufficient force, the rotator cannot be in the center. So for a given AMB, the force capacity is affected by a lot of things, like pole geometry, air gap size, winding turns, excitation current, magnetic path dimensions, nonlinear material properties, etc. So therefore, accurate prediction of the force capacity is a key step in AMB structure design. So the next question is why we use a surrogate model. As shown on the left diagram, it's a conventional designing for A and B system. It's an iterative designing process. First, you have an initial design or candidate design, and you analyze with finite element analysis to get the force of the initial design. And you compare with the performance or the requirements, whether it meets your requirements. If it's no, then you have to update your parameter. It's a circle, it's a loop. And until it finally meets your performance, and that's your final structure design. And as you can see, that's a problem. Conventional FEM-based design loop can be very time-consuming. So to reduce this computational cost, this work introduces a finite element-driven surrogate modeling approach. So this surrogate model is trained using FEM label data and then used to rapidly predict the single direction electromagnetic force capacity of the candidate before detailed Maxwell verification. So why single direction? Because if I only give one direction current, it's the minimum, it's the smallest force that A and B can produce. And if this single direction can satisfy the requirement, then the all direction can also satisfy the requirement. So I only predict one single direction. Okay. So next, I'll explain the features and the data generation. And as shown at the top, the workflow. Here is the workflow. As I said, this is a part of my big project, and my big project is using large language model or AI agent to design the property, the parameter of the A and B. So first things, I will give the LLM the design ranges, which means I use a JSON prompt and skills, all the things to give it to the large language model. Then the large language model assisted candidate a lot of parameters. So this 9 parameter is the basic parameter. So which means you can only use this 9 parameters, then you can define a specific A and B here. And I use large language model to create, to give me 632 sites parameter here. And then I use Maxwell 2D to analyze it, to get the magnetic force. And besides this 9 parameter, I also have 7 physical relative derived parameter, which means this 7 can be calculated by this 9 parameter. And why I did this step? Because in order to let the surrogate model itself to get the relationship between this one and the force, I will give it directly. So I can help the model to predict the force more easily. So here, F hat is the force, and X here is the 16 dimension, which is this 7 plus this 9, and Fx is the parameter to force function. And next, I will introduce what model I select and the evaluation process. So the 2 model families I evaluated in this study, which is Gaussian process, include GPMeter 1.5, GPMeter 2.5, and rational quadratic, which is different in the corner. And the trained ensembles include random forest, extra trees, his gradient boosting, XG boost, and cat boost. So why I use these two families is because they are more suitable for moderate size data, which means the size is not too big and too small. And my set data is 632. And I use these 5 things to evaluate my the metrics. I use these 5 to do the evaluation metrics, which is MAE and RMSE is the absolute error, and the WAPE and RMSPE is the relative error, which is the error divided by the real force and times the percentage. Well, here is the things that we did differently by others. Is geometry clusters are generated by k-means. So we didn't use this way. We didn't rank the sample from 0 to from the small to big, and take it randomly. That's the problem is that the data that you use to train is very similar to the data that you use to test. And if the model performs good, we cannot say that the model is not good, is not that good. But if we use the data that is different with the verification data that the model never see before, then the model is a good model in our opinion. So we use these opinions things to clarify the held out clusters in 10 clusters, and we put out one here to be weight be the last test data. And here's two tests we did. One is cluster block cross validation, which means we made a 5-fold cross validation. That these 9 clusters did the 5-fold cross validation. And another one is held out test evaluation, which means I use 569 data to train the model and then to predict the 663 sets. And I will show you guys the result. Here is the cluster block cross validation, which is a 5-fold validation, 5-fold result. As you can see, the GP model is performed better than the train. And I will discuss it later. And here the best is GPRQ, and here is the 1.5 GPRQ and GPRQ, which ME and these top two line is the absolute error. And held out test is more difficult, and the best model is GP matter 1.5. All of them is GP matter 1.5. So Gaussian process model are better suited for this MEA data size. The first thing is the moderate data size. As I said, 63 to MEA labeled samples is not too big and too small. It's very suited for the Gaussian process. And the parameter is a continuous design parameter, means the parameter is began from a small to a big, from a small size to a big size, the AMB from a very small size to a big size. And the electromagnetic response is non-linear but generally smooth, which means the reflection between the parameter and the force is non-linear. But if you change a little of one parameter, the force will be changed. And the 4 is matter kernel can represent finite smoothness and local variation. And the last one is tree samples are less stable when validation samples come from unseen geometry clusters. That's why they perform very bad in this situation. Okay, final, the Gaussian process model are better suited for this FEA datasets. And basically what we did is I developed an FEA-driven surrogate modeling workflow for 8-pole radial AMB force. And maybe future I will do the 12-pole or 16-pole. And second, construct 632 sample Maxwell 2D FEA labeled data sets. And 3, evaluated Gaussian process and trained sample models using cluster block 5-fold cross validation and held out testing. And also the GP matter 2.5 showed balanced performance, while GP matter 1.5 achieved the lowest held out test errors. And maybe in the future work, I will extend the prediction targets to multiple electromagnetic outputs, not only the force, but also the inductance, the fluid density indicators, and the power loss, like how many heat the AMB can produce. Actually, it's already done. And applying active sampling in high error geometry regions means I will expand my data site, not only 632, but to more big data sites. And the last one, integrate the surrogate model into multi-objective AMB structure optimization. And that's important, because that's the key point of my whole big project. I want to use AI or a large language model to help me to design the AMB. So how can we know which one is the best? You can use a multi-objective way to get the best one, like Pareto optimization, something like that. And in this way, you need this surrogate to predict the force quickly, so that the AI and agent can iterative design the AMD structure. Okay, that's all. Thank you.
Is there any question?
Maybe I can. As far as I see from the electromagnetic, because I also use Maxwell 2D and 3D program, electromagnetics is one of my working area. You have to somehow optimize the system, for instance, for the electromagnetic parameters. Let's say the aluminum, copper, and also permanent magnets, or when you use a core, electromagnetic core,
Right.
you should have different results from different materials.
Right.
So actually, as far as I remember, I did not get too much details in the paper on that issue. Maybe you can make an optimization on the materials used in this device, because magnetically you can have different responses from different materials.
That's correct.
Can you make a bit comment on that?
Actually, we use 35H300 scale in this case. I didn't mention, I didn't write it down. Because our lab has a real AMD system and it's used that material.
Okay.
Hope that answers your question.
Thank you.
Yeah, as an engineer, I'm quite curious about the force density. So in the reality, can you give us the rough number? How many newtons can this sphere take? Of which size? For example, 10 centimeter diameter?
Right, it can be range from 50 Newton to 1,800 Newton. From
Size?
From 45 inner diameter to 180 inner diameter. The inner diameter means here. I will show the picture. Is here, from here to here is the inner diameter, from 40 to 180.
And for the force is
From 50 Newton to 100, from 1,080, 800, yeah.
how about the dynamic control in case of very high speed rotation? Is that challenging to control this, or it's rather simple?
It's another topic of our lab. It's very difficult topic.
Control.
Yeah, we use PID to control the rotor. And when the rotor meets a very high speed, it will meet the critical speed and it will vibration. And that's another control strategy to suppress the vibration.
So it's manageable to control the
Yes. Yes.
I think it uses the eddy current effect here.
I know.
You know, because in
yeah.
but that's very good, technically very good system. Yeah.
For high speed, for high frequency, where the PID can still manage to overcome the force deviation there,
Yeah.
keep that is still in the center. That is my question.
Actually, this Maxwell 2D and 3D is very powerful for this kind of analysis, because
I
yeah,
know that. For the controller here, right?
yeah.
The air gap is changing quite a lot because of the PID.
Yes.
The PID is not a stable air gap change, and
Exactly.
the calculation is
Yes,
getting
exactly.
Therefore, he has to put the nonlinear. We have a BH curve, and this BH curve is a very critical analysis tool for this kind of nonlinear force determination. If you do not determine the BH curve with its nonlinear terms, so you cannot find the exact results. So probably they should give serious attention on that, I think.
I totally agree. Also, the sensitivity of the gap that is so critical
Yeah, yeah,
in our
yeah.
simulation because you can imagine if the shaft tiered a little bit,
Mhm.
then the force is totally changed higher
Yeah, yeah.
order.
Right.
And of course, in the current study, you haven't considered all the control.
Actually, I did a program that can automatically get the control parameter, and it tests in several real AMD systems. It's another topic. It's another topic.
Great.
Yeah, nice
Yeah.
work.
Okay, thank you.
Thank you.
So while the next presenter set up, I think Jakub Vandas. Yeah,
So,
the important stuff.
press, press photo.
Thank you. Yes, perfect. No, I want to photobomb this. Yeah. I know the cause. All right.
Okay, good.
Thank you.
Okay, next presenter, Jakub Vandas, presenting machine learning based classification and diametral estimation of milling tools.
Siz bu arada seçim içeriden sertifikasını siz vereceksiniz biliyorsunuz değil mi?
Onu verdim zaten.
Ben verdiniz mi? Hemen çok
Sıkıntı yok.
Fotoğraf çekelim.
Ya,
Ben Peter hocam mail atmış. Ücreti. Ben onaylıyorum, gönderiyorum.
tamam. Tamam. Ageta Bila. No. Let's see. Jakub on this. Yeah, this one.
Good morning, everyone. Thank you for being here today. Together with my colleague Agatha, I will present the work named Machine Learning-Based Classification and Diameter Estimation of Milling Tools. The main topic of this is to recognize the mills and the CNC tools, and also to measure the diameter, which is the most important in this process, and it is important to do it with a low cost, so you can apply it to the old machines and reduce the risk of human error. So let us start with the motivation. When we set up the CNC machine, we have to enter the information about the length and also about the diameter of the tool and also of kind of the tool. So it is important because when you use all the CNC machines, the operators have to do it manually and also to measure the length of the tool, also do it manually with the reference point of the spin wheel. So if operator will do it not correct, he can during the process we can also damage the tools and also do some collisions with working part and
it must make us also damage the machine. So it is very important. In other machines, it will be very simple to make it in a cheap way because we have also laser measurement systems, but it is very expensive for all the elder machines, CNC machines. Yes.
When it comes to the systems that are available at the moment, there are some sort of laser measurement systems, yes, but this type of measurement system require the high cost updates to the older machine, especially that are used in the fields that require, it was single part producing, for example, or a few parts that you need to produce. In this case, it might not be very good because you have older machine, but which is still good, and you change your tools every now and then because you have, for example, small magazine with tools, and you need, for example, 20 tools, and you change them very often. On the photo here, we have, for example, the broken tool. You see the chipping of this one. It was when it was made, it was a tool collision with the part, or
Yes, with the part, it was the photo of the two collision with the part, so you can see what's going on with
chipping.
chipping. Yes. Next. So what is the aim of the study? The aim of the study is to classify the tools we have also input into the machine, and also estimate the diameter. In the future we can also measure the length of the tool, which is also very important. But we have also analyzed the performance of our data, and we put it in the three parts. So we acquired the image data to classify the milling tools, and also to estimate the diameter from the image. And the most important thing is how the data is acquired. Because the CNC process is very fast, we have to acquire the image during the changing tool, at the point when the tool is changing in the machine. So that's an ATC point, and then we have to make a photo, and it allows us to classify the tool in a second, and also to start the process or allow to proceed to the next step. That's additional layer of safety. Yes. Safety. So we have made an experimental setup which consists of 4 conditions. In condition 1, we captured from a fixed distance the image, and in condition 2, we monitor in the fixed position, the position is repeatable, so that's easy to install the camera. And also we have 3 cameras to use because we're checking. Yes, we compare to the 3 cameras if it is important to HD webcam or something with more megapixels, or also to 50 megapixels. But we also compare to the next step. Also, we will talk about the effect of training with data size relation. Okay.
So that's our data set. Our data set consists of plant and mills, and also rounded corner mills, and also eval mills, and other types of tools to compare the accuracy of our algorithm. And also our data set is from 50 to 90 images, because when we make a data set of 5 tools, also each tool has 3 images to learn the algorithm, and also the next step was to check if it is better if we have bigger data set up to 30 tools and 90 pictures. So that was 3 pictures of one tool. And also we can make more, but if it doesn't matter, we don't want, because the algorithm can be overland also.
Okay, I will proceed now. Well, first off, the image processing. It was first we took the photo of the tool in the machine. Next up, the photo was sent to the computer. At least this was the case for this one project. We might do it, for example, next time in future on the computer. But we cropped the region of interest, right? So we only have the tool, the shank, and we see the whole tool, right? And it was converted to grayscale, so we have the corners, we see clearly the corners, and well, after that we used thresholding and edge detector and edge detection on this black and white photo, right? It allowed us to have the binary segmentation, and well, we could tell from this photo how many pixels we have from left to right? So we can have the diameter. This is shown actually in the third, in the debug window, right? The 2 blue lines. You have the diameter. Actually, this was actually the whole tool measured here, but I have only these two. Second, well, we have protraction here, so but I would, this was measured in pixels, not in millimeters for the whole project. Well, this process prepared the tool for the measurement, right? And also for the classification of the tool geometry. Well, the machine learning model itself, it was putting a process image to the resonant 18 model and adjusting the parameters of this model to the prediction of the tool class. We only had 3 output classes, which were flattened mill, rounded corner mill, including ball mills, and upper tools. Well, the resonant 18 is overall a big conventional network which is used for image classification. And this way, using this model allowed us not to create our own model in which we would need a lot of data of acquired photos of the tools, right? And so we have trained several models based on what Jakob showed in the data set. We have trained based on how big is the data set, and also how many epochs are used to train this classification. And the third, I would say, diversion were the web usage of webcam, the 12 megapixel smartphone camera and 50 megapixel smartphone camera, which showed us how much we get from there, right? Let's just be honest, grainy photo, normal photo, and photo with a lot of additional data, which can affect, and this is shown here, the machine learning model. For the dataset size, here are our it shows the influence of the dataset size on the classification accuracy, right? Here is the 5, 10, 15, 20, and 25, and 30. The best results were we got from the 15 and 20. I would also here hold this one thing that the dataset size, also the dataset difference, is important when it comes to the machine learning models. And in the bigger datasets, 25 and 30, we did not have more of the rounded corner mills. And however, these larger sets did not have a very bad, I would say, classification accuracy, though the 15 and 20 were the best. The difference between the flattened and the rounded corner were okay. So the balance is pretty important when it comes to the information. Okay, the diameter estimation results. I would say that the diameter estimation, well, for the small tools, for the diameter estimation, we used the webcam, which did not give us a very good photo quality. And we had like around, it was 9 millimeters per pixel for the better photos, so the average would be like that. And when it comes to the small tools, 2 to 4 millimeters, they had the photos were not good, and the edge captured were not old enough, were not seen enough for the algorithm to show, to create a line to create a line that could measure the diameter correctly in this case. And for this, the error level were pretty high. But with the bigger diameter, 5 millimeters and bigger, also the tool reflectiveness, we could affect these ones because we used for our photos the gray matte background, right? The gray matte background, and some tools, the gray tools, these ones and the reflective ones, were not detected with the also, and were not detected well because the reflectiveness was shown as the black element here. Yes, the more reflective surfaces. You can see here this one clearly. These are the black ones on the mill itself, right? So when the tool was small, especially when the tool was small, the black areas were near the edge. So and so the edges were like 1 pixel, so it could not detect them correctly, right? Well, the 10% for the low cost camera, which was really just a normal webcam you have, the 10%, around 10% for the 5 plus millimeter in diameter frame estimation. It was pretty good. This one is influence of image resolution and training duration. Well, we have here in image resolution the webcam, the 12 megapixel and 50 megapixel. I would say first off that yes, we got the best result for the 12 megapixel camera, but 50 megapixel gave us worse results, which could be by the fact that we had more pixels, which is more data that could, for example, have more errors here. And the webcam, which had pretty much low quality, had only the needed data. 67% for classification accuracy was, I'd say, pretty okay because, for example, the news used were 6R1, 6 millimeter, rounded 1 millimeter, right? Which were for the class of rounded corner reels. And actually, this one was correctly classified by the webcam as a rounded low field, right? So this shows that actually not the highest quality could give us the better classification performance. Well, when it comes for the training duration, the 5F 215 gave us good results. So one was 1 minute, and 25 gave us far worse results. This is probably due to overlearning of the algorithm. Yes, the algorithm was overfit by the images. It learned to just know what one type of data is. And probably if they use bigger data set and learn and more diverse, that's definitely more diverse, like 50-50 round corner with flat mills, we could get far better results. And the most important thing why we picked this topic, it was because it added a low cost safety layer for the older machine, and also it supports the operator, and the possible integration with existing older machines. It's pretty straightforward. You just can just, for example, plug in the camera, because some machines are just PCs, right? Running on normal systems, and you can just plug in the USB camera, put it in the right position for capturing the photo, and have a script in Python, for example, to stop the CNC program itself when it detects the wrong tool or the wrong type of tool or the wrong dimensions of tool, right? Also, but this one was not made, as I said. But it is possible to, for example, create such a program as additional layer. Well, the limitations of this presentation, I would like to say, is the small data set and messy balance. The blurry images can be set as limitations, but even though the images from the webcam were blurry, they had enough data to classify and to measure the tools. And the reflectiveness of the surfaces was help with this one.
So the conclusion is that it is also possible to make some kinds of additional layer. So it is very important in, as I can say before, in older CNC machines, and the older CNC machines are also in a very good condition right now, and many smaller factories or some kinds of people who making it on its own in the small businesses using these machines, and
Aviation, I would say, because when it comes to, for example, aviation production, you could have CNC machine client that uses, for example, 5 machines and creates 20 pieces of such part based on the CAD model of the part.
yes, so that's for small businesses, and we have to want to do some kind of ready setup, which probably can be installed in one position in the machine, and it will be working after the small calibration. So that's for that's all for now. Do you have any questions?
Yeah.
Thank you very much.
Is there any question?
Maybe I can
Yeah.
have a question. Actually, you have a camera image for 50 and also 12.
Yes.
You know, I did not get the case because I expect that with the better
More
resolution you
information,
should have much more
not
accuracy.
necessarily.
What can be the reason for that? I mean,
Well,
your
when
comment.
you have the higher resolution, the picture is bigger, right?
Yeah, yeah.
So the picture may have more, I would say, distortion, because it has more image data. Well,
Which makes the corner in the review
Mhm.
can be not correct for the algorithm to really make,
Hmm.
and also the time of processing the images is higher. So
yes, definitely.
So
And learning.
but the CNC machine couldn't stop, and I think what the tool is, but it should be done in a
And second of all, I would say that's not
200 of milliseconds and go or not or stop for the operator. And operator have to confirm if it is correct tool or not. That's only for reason avoid the collision when something is in other dimension. And the other dimensions in the CNC machines, and reality is in reality there is other dimension of the tool. For example,
So
weight and diameter.
it is not related to the machine memory or something else. So it is
could be,
maybe.
yes.
yes, but as I have said, some machines that are used are, for example, just a normal Windows PC with additional program, right? Or Linux machines.
There are some kinds of hardware machines, for example,
Because image there are very specific programs codes for image processing, so that's very important for your case to use the correct one for the sensitivity and also the accuracy of the images. Okay, thank you.
it could be that when we make the old database older,
Mhm.
but from ResNet 18,
Yes.
it would be better, but it is very time consuming for now, so
I see.
And
But data points are also important. You get, I mean, if you have much more data, then you can have much more accuracy, I think.
yes,
Mhm.
definitely. And well, as I said, we are based on the existing network to process, to assess, to process the images, right? And so we are adjusting it based on what we have here,
Mhm.
based on the, for example, 9 photos of the tools, and the tools, 2 photos were taken in a little bit different angles. So yes.
Okay.
Oh, it's about the 50 and why the 50 works worse. I would also say that when it comes to this application, I would prefer the low-cost version because, as I said, this is mostly for the small workshops, yes, that work with old machines. So why would the small workshops want to buy the newest, for example, smartphone plugger? No, they want the cheap solution,
Mhm.
and that one that will work.
Okay. Thank you.
Yeah, thanks. Due to the time, I think it was the last question, or should we ask?
Yeah, if there are any other questions, then we can get. We have time. No problem. We have time. We really have time. No problem.
Actually, it's very similar to your question. I also doubted a little bit why the 50 megapixel
It
is less accurate than that you. I guess maybe you need to improve the algorithm behind.
Yes,
Of course, for the transition pixels, you need quite clear definition of the threshold value. But in our opinion, it must be accurate and 12 from physical behind. Maybe the algorithm behind it needs to be improved
yes,
or
improving.
checked.
Yes, how the addition, how the classification.
But my simple question is, how large is the size for per pixel? In your case, roughly how many micrometer
Micrometer.
per pixel?
Yeah, we went actually with
Because this is the whole size of your pixel.
Yes.
But you have, for example, 2048 times 1024 pixels, and then compute back to the size of the
Yes.
of the real image size.
Yes.
You have always a correlation. One size or one square of the pixel stands for how many micrometer. Do you have this number in mind?
No, actually these ones were like where that we measured the picture, right? The pixel. How many pixel it is when it comes to diameter, and we used this number and the real life life, and it's real life size. The diameter we measured with the caliper.
I think it's 1 over the second column. The question, the answer is
Yes,
1 over
this
the
is
second.
mean pixel per millimeter.
On the diameter.
Yes.
Almost 0.1 millimeter for the.
One pixel,
1 pixel.
0.1 millimeter. That is too rough in our opinion.
Yeah.
Too rough. So you need for this diameter, for example, 2 millimeter diameter, you have only 13 pixels. So you
Yes, so the camera quality.
So the resolution is 0.1 millimeter. That is too rough in our opinion to capture the wear.
Because even when we're also with that, there is a cooling fluid. So that's additional problem.
Yes, in machines there is a cooling fluid that would damage the camera, for example. So this is
Or
also
effect
why
on
we
the-
don't
on themselves
want
also.
want to use the more advanced cameras, right? Yes, because you can go ahead and use, for example, the camera that costs 100 euros, but you can also try the 10 euros.
I agree on this aspect, but I mean from scientific point of view, if your resolution is so rough and
Yes,
your estimation is just very rough at the end, how can the operator trust your picture and the
Yes.
evaluation after that? I don't care on how much is a more expensive camera, I just need the accuracy, right?
Yes, the accuracy should be first.
Maybe also one question regarding the first picture array scale that you showed for the meal bits. If I remember correctly, when we want to measure it, we need to turn the mill wheel to make sure that we capture the biggest diameter we can. So because if you do this pattern, you could actually capture a diameter just with one-time caliper that is much lower than the actual cutting diameter.
Yes, but when you making that, when the machine is going so on, it's important to classify the diameter of the tool. Like for example, there is 9mm tool, but our algorithm told that there is 8.7. And that's enough because we know that that is within 1mm, so it's classified to the 9mm.
So you don't care about the actual number because the title seems that you want to precisely tell which diameter it is. So that's a bit maybe misleading. But yeah, yeah. Thanks for the explanation.
Thank you.
Please.
You want it to be in the picture?
You want one?
Oh, sorry.
Yeah.
Yes.
Essential.
Son paper.
Yok. Şu şimdiki bir tane daha var. Ondan sonra
Thank you
sana
everyone for
yapacağız.
joining. My name is Alborz Almanikisaristani. I'm from Research Center of ABB in Germany, presenting the floating spring drive load break switch for sustainable free switchgear. So throughout this presentation, I try to explain different part of this sentence or partial sentence, and then also show what we achieved in this project. So, first of all, what is the load break switch? You're all familiar with the light switch at your home. It's some form of disconnecting the line or the electricity in your home. Assume that now you're in a city and the city needs to somehow block or stop the electricity for some portion of the city or to factory, or you're, for example, in a power plant, a solar plant. At the night, you want to turn off this power plant. You don't want to be connected to the system. So, in a medium voltage load break switch, range of 12 kilovolts to 36 kilovolts, something in that range, you need the devices to be able to connect and disconnect the line safely for you. So that's where the load break switch comes to the play. These devices need to disconnect and connect the line really fast. So the mechanical operation needs to be really fast. To just give you an idea, at the end of this type of tip, we need to achieve 10 meters per second speed to be able to break and connect the arc. If we go above this or below this number, this arc burn for a while and your whole substation can explode. So it's really important to keep the certain timing for breaking and closing of the arc. A normal load break switch had 4 operations: one making, so making the line so basically electricity can pass through, disconnecting or breaking the line, and one operator or technician mode, which is called earthing and unearthing. Assume that you're in a city, the power connects to many home appliances, and in each of them there is a capacitor. And then the technician wants to do some modification on the device and touch the system in an off state. All the capacitor on the downstream of your system will electrocute the operator. That's why we need this earthing mode to make sure that we discharge any remaining electricity on the downstream of the line. So that's quite important. And this actuator consists of this drive consists of actuator, which is mechanical device, electromagnetic device, providing the motion for the switchgear mechanic. So the switching mechanism, which is actually physically connecting, disconnecting the line, and the gas insulated tank. So the topic of SF63 is important for this gas insulated tank. This tank has many functionality. It needs to make sure that between the poles, the three phases that we have, we don't have any electrical jumping, or in this case partial discharge. So there is, due to the phase shift of the basically voltage, we might have electron jump from one pole to another pole. So this gas should be act as some form of dielectric to make sure that this behavior couldn't happen. And also, due to the pass of such a high current voltage through the line, we have a lot of Joule heating. So basically, this line can easily, the atmosphere can get to the 100-degree inside this tank. So it also should have a good thermal capacity to not expand so much. Otherwise, this tank needs to hold a high pressure. So it's also quite important. And also, the main other function of this thing is basically to break the arc. And we have many technology to do that. One is using the splitter plate. All this technology that I'm showing you is work based on distinguishing the arc in a way by elongating the arc. So the more the arc is burning, the distance the arc burning, the higher chance that we can break it. So this splitter plate idea is that you have a blade and multiple plates. The moment the arc starts burning, you push the arc toward this splitter plate. So one uniform arc separated to 10, 20 different smaller arc, which elongating the length of the arc. And as a result, you basically distinguishing the arc. The second one is buffer base. It's quite patented by ABB. It's a method used mainly by the ABB, which is while making the contact, you create a cylindrical that push the airs to the arc. So you basically by puffing into the arc, you elongate the length of the arc and causing the arc to break. And the third one and most common one in a basically higher safety device used is a vacuum interrupter. So basically at the point of contact, you create a vacuum bottle. And it's an ultra high vacuum. So it means there is almost no molecules between the two contact. And as a result, by just separating slightly the contact from each other, there is no chance that electron can jump from one anode to the cutter. So that's another method. So the first two methods, or a splitter plate idea, is the main method used in the load break switch. It's the cheapest one. It can assemble really easily. It only works with certain gas, called SF6 gas, which is really bad for the environment. So SF6 is kind of fluoride gas. 1 kilogram of that is equivalent to 23,000 basic kilogram CO2, which is by European Union banned. And later on, overall, by US and China is also banned. So from 2026, we couldn't sell any device having SF6 inside. It's like, if you remember Freon for the refrigeration, that's also a similar class of gas. So it's banned for even industrial use. So this ban came, and now we need to come up with a new solution. So one of the solutions is to get a similar behavior to increase the pressure inside the chamber. Previously with SF6, we could use with 1 bar pressure, so gauge, 0 bar gauge, we could work with SF6. But if you want to go with the dry air, so the air that the moisture taken out of it, we need to increase pressure to 2.5 to 3 bar for the application. And this increase of pressure means the drive needs to provide higher amount of energy, and we need a different type of energy releasing for such a system. That's why we come up with our new design called floating spring. First of all, we have a concept. The concept is that we have a compression spring hold between two basically lever arm. By turning one and locking the other one, basically we charge the system, and at some point of time via cam system we release the trigger and delatch the output. So we charge a spring, and via a mechanism we trigger it and release the energy of the spring at once. And via that basically could connect or disconnect the line. Okay, the methodology for this, for basically designing such a drive, they start with the concept, then we do the analytical calculation using MATLAB and simulating, having a modified or light multi-body dynamic simulator to check all different conditions, different size of the spring. Of course, the spring is taken from the data sheet, so it should be a real spring. It's not just a number K and we load for a system. So we just put different type of real spring, and then we basically based on a viable solution, we detail design the drive component. And after that, we had a multi-body simulation in Adams to show the performance of this switch if we can achieve to the speed that we wanted. And basically to prove it here that we could. And then later on, next step is the experimental and validation. So we build a prototype of this system and validate it, basically with all the experimental method, our Adams simulation, and our simplified numerical simulation. So again, as mentioned, the concept is having a compression spring between two rings. One of them has output latched, and we charge the spring, and at some point of time, we release this spring. For our analytical calculation, we play with a lot of parameters. The length of this lever arm, the initial or depth length between these two link angles, and the spring length, preload, different stiffness and different size of the spring based on the real value. And we basically put it into the one dynamic simulator, so basically ODE solver to solve the whole equation and see how much angle we can travel via this mechanism and how what would be the speed or the timing between for the operation. And out of that we actually could come up with a solution with detailed design the different components of this drive and showing the different phases are achievable, so we can have from off mode, charge the system, and then go to the on mode of the system. And for testing it, we need to also build a dummy drive, three-phase drive. So as you can see, we actually 3D print the whole thing here. It's actual size of the medium voltage drive. Pole distance of 120 millimeter. And the idea is that this switch has this blade has a spring-loaded element in between, and when it gets to the fixed contact, they always with a certain force pushing against the contact. And this part is also there is a connection element that rotates the whole three phases together, which is connecting to our drive. And with this dummy switch and the drive, we run a simulation. We run a simulation for one closing operation, and we could show that basically the delatching happened and the whole system, whole switch release and connect the line. Okay, after that, we basically build, after showing in the multi-body simulation that the system works, we produce the drive, and the important thing, as I mentioned, we want to see what would be the speed of this drive. So we connect the encoder on the output of this shaft, and this is charging the system and record the angle coming out of this basically moving of the main shaft. So that's actually a picture of the actual doing the experiment. So the operator via the handle charge the system. That's our encoder running in this set and shows the system actually can do the closing operation. And after that, we basically measure the experiment value and compare it against with the simulation and the initial numerical simulation. Of course, there is a quite difference in how we could operate an initial different speed, but for the operation of the system, only the speed at the end point of the system is important, when the arcing can happen. And over there we show that we have less than 2% error in the speed of the contact for the switch. And with that, basically show the system works. We could develop floating spring actuator drive, verified in light simulation, later on in multi-body simulation, and also show the performance with reduced model or reduced prototype of the system. And that would be the last slide.
Okay, so it works. Yes?
Yeah.
Okay, great, so congratulations. So technically it works. Do you just want to run through the techno-economics? You know, this is we were chatting, the major competitor is Schneider Electric.
Yeah.
How much better than the Schneider Electric solutions is your solution?
Yeah,
Is it cheaper? Is it more reliable?
That's actually a good question. This is just the mechanical performance of the system. For the switch gear, there is one big aspect is the electrical performance of the switch. So, job of us as a research center is just develop the idea and then hand it to our business unit. They develop the full product out of it. So for us, it's just to come up with the modularity, new modularity of the design. Of course, we look into it. Definitely, we want to have a product better than a Schneider Electric. In some aspect, for example, for us, we work mainly on the patent. And the publication is kind of blocking our competitor. So this type of event is for us to blocking our competitor to not use this type of idea.
Okay, we understand.
And that's one thing we think it's valuable, or our manager thinks it's a valuable idea, but maybe we don't want to work on it in the next 10 years.
Okay.
And that's why we block it. And that's the idea.
Never stuff. Thank you. Congratulations.
My question maybe concern the spring, because the stiffness of springs can change by time, because when you use so often, so from time to time, maybe after a few years, the stiffness can change. Can make any difference in your results? Maybe it's the matter of time, maybe, I don't know.
That's actually a really good point. The reason we use this compression spring exactly for that point, because helical spring has the most material usage for the compression. So when you compress, you use the whole material deformation for this operation. So the chance of fatigue or trippage in this compression case, but fatigue on such a type of spring is much low. And also have in mind, this type of actuator needs to operate 10,000 operations maximum. So it's not like it's not possible to compare it with the spring that you have in your car. That's open the exhaust valve, injection valve, almost I don't know how many times per minute. And these are quite low working system, this type of system. But the lifespan is quite long. So this system should work over 40 years. With one installation should work 40 years. And the thing is, with compression spring, we don't have that much variation. We have, of course, one initial variation from the data sheet, but it's considered in the design. So we don't have just one speed, we have a band of the speed, and we calculate 10% of lose of the stiffness, and the spring should be inside that band of the speed, and then it's good. These are quite many products of this, and should be one-time design, really cheap, and then installed on the system. That's we don't need to worry about it. That's why
Okay.
the design need to be a bit robust in that sense.
Yeah, that's good. Maybe, yeah.
So is there a vibration switch because the pin will connect and disconnect, connect and disconnect due to the switch?
The vibration is quite, you ask for vibration.
So when you switch,
Yeah.
and you just use the spring to switch, right? And the switch might damping or
Okay. That goes back to the level of the energy that we need. So for different level of voltage, we have different energy for this spring. For the low level, usually the internal damping of the spring is enough for capturing those back and forth operation, and also the housing in many of these cases is thermoplastic. So it acts as a form of damping, structural damping. But if the energy goes high, for example, 200 joule, or for high voltage, 200,000 joule, 200 kilojoule, for the real high voltage one, which is you're not working with, then over there we actually use active or passive damper element, real damper, the hydraulic damper in the system, to basically at the end of the operation dissipate the existing energy in the system. But yes, it's completely valid. We have this vibration, but we usually try to capture it by friction or friction dissipation or damping of the structure.
do you use a or
Yeah, this spring, one of the challenge was we want to buy it. So we have a data sheet, for example, in this case we have around 10,000 different springs in the size that we want, and we feed it into our simulator to check, because also the diameter is a constraint. If the diameter is too high, we need to build all the linkage around it to adapt to this diameter. So all this is considered in this work.
So another concern that from the point of electricity,
Yeah.
I mean, in one of the slides you showed the photo of the system with 3 phases, yeah?
Yeah, okay.
My question is that because of the 3 phases, the separation of each part should be very secure, because, you know, voltage can yeah, you know already.
You're asking a really
So,
good question.
have you tried the electricity simulations on that, or?
Yeah, it is actually, there is one specific point of time that we need to operate this switch, and it's a huge issue for all the business, I would say, especially in AC. As you know that we have 120 degree phase shift between the 3 phases.
Mm-hmm.
So when we can do this operation of braking, when we have this zero crossing, so we have the minimum voltage. If we do it in a high voltage, the arc burn through whole operation. We need to do it in this zero crossing, and this zero crossing, we can guarantee one pole we don't have much arcing, but the other 2 poles, we are in the middle of the cycle, so we have some form of arcing. And all this trouble of braking mechanism is for those 2 other phases that is not fully in a zero crossing. There are many methods. We can have an actuator in load brake switch. It's not really issue because it works in a nominal condition. It's not in a short circuit condition. So with that, we can rely, even if we have some arcing, nothing will happen. And almost all the business, we have a standard, and if we follow that the standard, we're fine. So if one of the pole is in the zero crossing, what happened in the 2 other pole is not lethal for the breaker, I would say. But for switchgear is actually a problem, and we have cases that we have different actuator for each, and we try to trigger it in this sequence. So each of them do it on its own zero crossing. But even over there, there are some possibility to shift this zero crossing or via power electronic handle that create artificial zero crossing for each pole.
And also another point is that to selection of the, you know, insulating material, which kind of material for the installation will you use? So that's another point.
The development is only this partial discharge analysis. So how the shape of this housing should look like, that we don't have this arcing, or even if we have, how to capture it. The whole system can still continue operating, because for some of the application, especially closer to the power plant, we definitely have this partial discharge, no question. they actually make ducts and a structure to this explosion that happened, they conduct it to outside. So the whole, they don't strain the mechanical component. So there is a valve, basically there are explosion valves that opens and this expanded air goes through that exhaust to the outside.
Yeah.
These are
And
also quite-
all the system is covered by another shelf or housing, or this is
system
open?
Is one part of the panel, and this
Uh-huh.
panel can come in a minimum 3, maximum whatever the customer wants.
But you should put a housing,
Yes,
all of them,
the
because
housing.
otherwise you can have, from rainy days or snow, you
Yeah,
can
of
have
course, of course.
yeah,
and
problems.
These are all indoor applications. So we
Okay.
also have one set is completely outdoor
Yeah, yeah.
over the pole, depending on which country we are. There are different ways. For example,
Okay.
in the US, there is a huge issue that all this switch is overhead. So on the line,
Yeah.
overhead, charging it is quite complicated. All these aspects is very complicated.
Very good. Okay. Thanks. Other questions, maybe? No?
Other questions?
Okay, thank you. So maybe I can give your certificate.
Yeah.
Thank you very much. So there is, yeah,
The
maybe you
next
can
one,
announce.
Gianni, is to my colleague, good friend.
And after this one, we have another
Yeah.
talk. This one, because
Yeah.
yesterday she has problem with the flight, so
Yeah.
after this we will have.
So everyone, welcome to my talk. Actually, this topic is a continuation of what I was just now introduced, but with some kind of more. We'll show you 2 more actuators and also 3 new switch mechanisms. The title is how to basically pair the actuator with the switch, and then to check the evaluation. Why we do this simulation? Basically, this simulation best. You can ask Abbas, so for his presentation, he spent maybe 10,000 euros, of course, prototyping, testing centers. I paid €0, right? Because I just did the simulation. It's a joke, but it is quite important in our research center that we carry a lot of simulation to have a prediction of the performance in advance before we go to the prototyping process. It is quite often needed. Yeah, as I mentioned, we come from EDB Corporate Research Center in Germany. Yeah, I will give you a very quick content introduction. So I will give the motivation and then show you the switch mechanism used in our load break switch and also the new actuators, and show you the results as well as the conclusion. As I was already introduced, the load break switch has the main function of breaking, closing, and opening in nominal current. And you can see this is the left-hand side is one typical indoor load break switch used in ABB, for example, for the arc furnace, also for the transformers. Sometimes the operator needs to shut down that line in the night to make maintenance. Yeah? But pay attention, this is not a circuit breaker. Circuit breaker means that in case of short circuit current comes, the device needs to take action immediately by himself, automatically. That is circuit breaker. But this is load break switch. Normally the operator turns it on or turns it off by himself. And then how does it look? Very simple. Like all of the switches you have at home, we need to make the moving contact here display to close, to touch the fixed contact. That's all, and then separate them. Simply said, but the main problem is that this is just the closing and opening operation, you can see, just to make the moving contact connected to the closed contact. In the reality, due to the arc, you can imagine the voltage is 36 kilovolts, and then you just open or close, open it very slowly, the arc will continuously happen, and it will burn everything inside your chamber. So the motivation or the older technology is that we use the SF6 gas inside this closed chamber. This is a very good gas, of course, has many functions, but due to the environmental pollution of this gas, the European Union banned this technology from this year. So from now we are not allowed to sell this product. Then we need somehow to make innovation or new technology on the load break switch. The current technology is more or less, or also from the competitors, is based on the high pressure. So now we pressurize the tank until, for example, 2.5 bar to have the isolation property. And of course, also to make the opening or closing more faster than earlier, due to the vanishing of SF6 gas. Yeah, this is basically the motivation why we need to design new actuator. As you can see, basically the drive, but as well as the switch mechanism to adapt to these new requirements. Yeah, and before I go to the actuator design, I want to introduce you very quickly 3 kinds of switch mechanism used in the load break switch currently in not only in ABB, actually also in Siemens, Schneider, or of the other competitors. The first one, as I was already introduced, we use the splitter. Basically, you cut the long arc into several small pieces, and then to vanish that one. That is the standard splitter blade. The cheapest version, of course. Then the second one is using a vacuum interrupter. This border we call the vacuum interrupter. Basically, inside is high vacuum, like 10-6 or 7 Pascal. It's really high vacuum. And of course, for this mechanism, maybe just a side note for you, how does it work? So basically, we do both for connecting and opening. We firstly go through the vacuum interrupter, the current. So the current is through firstly go to the vacuum interrupter, and then to the fixed contact. I mean here, if you can imagine the current comes from here, for example, it goes first through the vacuum interrupter, and then to the moving contact. You can imagine inside the separation of moving contact and fixed contact is now happening inside the vacuum interrupter. Since it is a vacuum, it will not generate arc. That's the fancy thing here, why we use this vacuum interrupter. And after the blade is totally separated from the moving contact, then we disconnect again the vacuum interrupter. Now, of course, in this whole process, there is a handover mechanism. We need to hand over somehow the current, firstly to the vacuum interrupter, and then to the fixed contact, as well as for the opening process. Of course, I cannot show you all of the details due to confidentiality here, but that is the best function. Normally, those vacuum interrupters are used in circuit breakers, not in load break switch, but we here use these high vacuum for this also switching load break switch. Of course, the cost will increase, right? And then the last one is also a very interesting mechanism. We call it the puffer technology. How does this work? I will show you the next slide, the detailed functionality. So basically, we blow the air during the opening. The arc mostly happens. We blow the air very strongly into that arc spot to distinguish the arc. And here, what I want to show you from a mechanics simulation point of view, the loading profile of all of these switching mechanism. You can see that the split plate basically has the lowest torque against the angle, because basically this is only the weight and the friction force inside. And then the shunt VI version, we have, of course, all of this effect of a split plate, but as well as we need this handover mechanism. That is this jump here between. This jump is somehow the handover to the shunt to the vacuum interrupter. Then we have a sudden jump of the torque. And then for the puffer, of course, it is velocity dependent, right? If you open it faster or slower, the pneumatic force is different. Of course, this plot is given for a constant velocity, but in the reality, it should be some kind of parabolic shape of the load. It is velocity dependent. And then we also have a motor for this the pneumatic puffer force. And then now, since I already introduced the first two mechanisms, I want to give you a little more detailed explanation of the puffer technology, since I think it's quite interesting for you. How does it work basically? Now the previous slides just show the blade shape as moving contact and the fixed contact like this, but there are also some other versions like this. You can imagine the fixed contact. This one is a tube, it's a copper tube with these two length legs, yes, tube, and then the moving contact inside is another tube, but with this shape. It's another tube here, but with an opening here. And this is sealed somehow like a piston here, these two positions. And then now, let's go to the second picture. For the opening process, we pull down the moving contact, right? We pull down the moving contact. And what happens now, you press basically, you press. If you pull down the moving contact, you also pull down the piston here. Right? You can see this line. And then the air in this closed chamber here will be compressed. And then by doing this, you blow somehow the air to the arc point. You see the arrows of the airflow here. So during the opening process, you press the air and then it blows the arc directly. And you just to eliminate the arc. I'm not sure whether it is complicated. But the main idea is to really use the high pneumatic force blowing the arc. Yeah, now we have three switch mechanisms. After this, we need to know what kind of actuator works perfect or best for which switch mechanism. Then by doing this, we have a comparative study of three different kind of design concepts. Of course, please be careful that this is just really a proof of concepts without showing the detailed designs behind. We have also designed all of these drives in our lab. But inside this scope of talk, I will show you just the concept of the design. So the first design, as I was already introduced in detail, the floating spring mechanism. Basically, you hold the, for example, the blue bar, and then you charge it, and then you suddenly lose or delete it, and then the hover will move to close it, and also for opening is similar. And the second one is, I think it's easier to understand. Basically, we use the revolution joint here. The red bar will rotate, so you can imagine the solid line or solid spring is at charged position. It is at charged position, and then you somehow delete it, and then the spring will get longer, so release the force, and then the red part will rotate. That is the second design. And then the third design is based on the cam mechanism. Also quite similar and easy to understand. You have the charged position, the solid green line, and then during the opening, you basically push the red bar to make it rotate. That is the mechanism behind. I plot the design roughly with purpose like this. It looks ugly, but in the reality, it's the real size. You can see that the floating spring mechanism and the revolution joint have relatively compact size, right? And for the cam mechanism, because we need to use these contact point. Actually, this is not advantageous for the size. You see that the size is significantly larger than the first two. But by the way, the springs used here, all of them have the same length and the stiffness. So this is real size comparison here. And of course, they are based on different mechanism. But the torque profile, you see that also will change, right? So you can see that for the first design, the floating spring, it has the highest torque at the beginning, and then after releasing, the torque decreases. Yeah? And then for the revolute or for the cam mechanism, you see it has the lowest initial torque because the lever arm. You can also imagine that the lever arm, we start from this position. The lever arm, the force is horizontal, and the lever arm is so short. So the torque is quite low at the beginning, and then higher at the end. Somewhere in the middle is the maximum. That is the green color here. And then for the revolute joint is somehow between these two drives. And which is important to mention that the surface area below these three curves, basically the released energy here, yeah? The surface below the curve is the released energy to the system. They are the same. So we need to know now, under the same condition of the spring, a preload force, the final force, so that we have the same area, and then the same energy level for the release. Which drive works best for the previously mentioned switch mechanism? That is the whole motivation for this study. Now we plug all of these 3 times 3 combinations in the simulation tool, and then we have this result. From this curve, you can see that for closing operation, basically the floating spring mechanism works the best, the fastest closing operation here. And the second one is the revolute joint, and the mechanism, and the last one is the cam, which means for the closing operation, we need better at the initial of the operation higher torque. The higher, the better it accelerates at the beginning phase quicker, and then slow down a little bit the torque. That's exactly also the curve indicates at the end. But very interesting, and of course for the closing process it's less critical for us in the reactor, but the opening process is even more serious because the arc normally happens more often there for the opening process. And then this is now interesting to see. You see that the curves cross each other, not like the previous closing case. For example, if we combine the cam mechanism with the puffer, the performance is somehow better if you combine the revolute joint with the puffer mechanism. That is not exactly the same pattern as previous closing operation. So basically we need to now, from research science point of view, we need to tell our business unit where they produce the product at the end. If you combine, for example, the cam mechanism with the puffer switching, you need to pay attention to the performance, and because this is the best one. Or some combination is the worst case. And that's the information we are responsible to tell the business unit. Because they are normally designers, they draw the parts, they realize our concept into the products. But we need to tell them what are the drawbacks and advantages here. That is the main information here. And besides this point, currently we are also working on designing more sustainable drives. This is another very, of course, also a little bit political point. We need to make our products more greener, basically less CO2 pollution to the environment. And then by talking this, we need to really, from the draft of design to end of the life of the product, we need to consider all of these process when will CO2 be produced from the raw material, the transport, to forming the parts, to assemble it, to use, end of life, recycling. All of these, inside our group, we have 2 colleagues who are experts in developing this method for the sustainability analysis, and he contributed for this study the performance and the sustainability scores here. As you can see that regarding the performance scores, the first 2 pictures, Of course, the float spring mechanism combined with the split plater has the best opening velocity. We are talking about the opening process. And the cam mechanism combined with the puffer has the lowest speed performance. And this is also in good agreement with the opening time. But regarding the sustainability, so we call the global warming potential, over the velocity, actually the revolute joint combined with the split plater has the greenest, so to say, design combination, and the floating spring design together with the puffer, as well as the cam together with the puffer, has the highest global warming potential, especially due to the size of the cam mechanism here, that we are producing something that's less sustainable. Of course, the whole evaluation is quite, reliable, dependent on database from the guidelines. So which material has which kind of CO2 production per kilogram. All of these data somehow we need to collect first from outside. Yeah, with this I would like to conclude my talk quickly. You can see that the joint optimization is needed for the combination of actuator and the switching mechanism, as well as the material selection. And no single actuator switching pairing is universally optimal. We need always to give each individual evaluation to the end. And the closing performance in this study is mainly governed by the actuator torque profile, as I introduced earlier, since the speed is less relevant there. But the opening performance is more critical and more sensitive to design choices, whether it is a puffer mechanism or shunt VI or just the splitter. Yeah, the last point regarding the environmental impact, it must be evaluated together with functional performance. The fattest solution is not always the most sustainable, and normalized indicators such as the global warming potential for opening velocity support better design decisions. This is also something we need to tell the division, the business unit, that if you really focus on the sustainable design, then you should maybe balance somehow the performance and the global warming potential. Yeah, with this, I would like to close my talk. And thank you very much for your attention.
Any question?
Actually, I have an additional, maybe I am wrong, maybe not, but in some papers I read that this discharge, when discharge happens, and ozone, I mean O2 plus O is coming together. So an ozone molecule has been generated.
Yeah.
This can also help for the climatic changes. Have you ever heard about it?
Yeah,
I
know
mean,
that
that's a positive.
I know that during the
Yeah.
discharge, the arc generation process,
Yeah.
there are some,
Can
O3
help for the.
O3 generation
This is
there.
positive.
Yeah, O3 generation there.
Voltage level is quite different. For example, for the lightning that happened, lightning is quite high voltage compared to what we have here.
But
Arc happened
But in the lightning, there are also very small filaments with smaller voltages also. So I am.
I'm not sure whether there are some statistics about the how O3 generation due to this arcing process worldwide. But
Maybe you can also make some experiments on that issue. Maybe. Yes, but.
This is arc physicists.
Yeah.
Chemists.
That's also interesting.
Also, the material inside, I think, all oxygen free. So
Yeah.
dry air is not just moist; it's actually a different chemical. This different chemical. The name is conventional name is dry air.
But
I think they remove mainly nitrogen or CO2 in that case.
But
So,
a certain percentage should be generated, I think.
Yeah.
Yeah.
But could be very low. In comparison to the thunder, if one thunder gives how many tons of O3, I don't know, comparing to this switch device.
Yeah.
But it's an interesting point.
yeah.
Thank you.
Any further questions?
Questions? Okay, thank you.
Then I have the
Chairman, you should present it because they're both.
We,
Are you co-authors?
indeed, we have
Yes,
many
yes.
photos together.
Okay.
And we have,
conflict of interest.
we have had many.
Okay.
Ah, okay.
Both of you.
Yes, 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 sure.
Yes, sure.
All right, perfect.
Now you can.
And then, okay, perfect.
Actually, I would like to, because there was yesterday's program, Sana Amgerdi has had a problem for the flight time. So she's here right now, and for the yesterday's event, ECRES conference, she will make the presentation, and then we will listen to her, and after that the session will end. And after that we have a lunch.